Danie, can you? Oh, perfect. Thank you.
Is that good? Can you hear me?
Yes. Thank you.
Okay, thank you very much. Thank you for the invitation for today. I have to acknowledge my co-authors, Albie Brits, Alexander Crostingham. Obviously, this team, the whole entire Ivanplats team has done a lot of work over the past 9 years, basically, and even more historically. So this obviously is quite an important project for the company. I just thought I'd put up this picture here. This is a chunk of rock that came out of our shaft number 1 in 2018 September, when we intersected the actual high-grade reef section. And you can see basically a pigmentoidal peroxenite at the base. There's a lot of sulfide, chunks of sulfide, composite sulfides in there. And then that red line shows a very thin chromitite stringer. You can see how that stringer sort of undulates, and then above that into a feldspatic peroxenite. So to us, that's where this whole thing started. Obviously, when we did the drilling on this project, the exploration, we saw this chrome stringer on this very important contact associated with the mineralization. Basically, my talk is going to be about this, what we found here through all this drilling that was done. So Ivanplats is part of Ivanhoe Mines. We listed on the TSX and all the associated regulations thereof. Our share price is pretty low at the moment, as everybody else's. So this first slide just shows the Bushveld. What I think is important here that we need to look at is, and I tried to find platinum-palladium ratios in the literature across the Bushveld when I did this. And you can see, obviously, you can see my cursor there on the western limb where the ratios for platinum-palladium was fairly high. It's mostly above 2. And as you come across into the eastern limb, it goes down a bit. It goes below 2. And you come around this northeastern corner into this sort of western part of towards the Bedela on the eastern limb, where there's fairly low ratios in places. And then obviously we move across this Tabazimbi-Murchison lineament into the northern limb. And I found Ian's presentation on the structure very interesting, and also Nicole's on the Merensky Reef and all the lithological and thickness variation. So that's the type of things we focused on. Into the northern limb, you can see that area there. That's where the Turfspruit, Makalakaskop, Ivanplats properties are. So if we look at the average Platreef published platinum palladium ratio that was calculated across this entire Platreef zone, which can be fairly thick, in places a couple 100 meters thick, you get a fairly low ratio, especially if you go down from the top below the main zone into the lower parts of this mineralization. It goes far below 1, actually. It goes down to about 0.5. But when we look at Ivanplats on our property, and as we've defined the reefs recently, as on our publication in 2019, where the chrome stringer is situated on that contact with the pegmatoid, that first sample in our database, which contains hundreds of thousands of assays on this property, the ratio actually is fairly high, and it's fairly similar to what we're seeing in the Eastern Bushveld. So I just want to show you that, and I think that's one of the important things. The Platreef needs to be redefined. What is Platreef? And that's what I'm going to try, part of what I'm trying to do today. Okay. So when we look at the northern limb, as you come from the south, we come across from the eastern limb into the southern part of the northern limb. You can see the peroxenite units. The stratigraphy in that area is fairly similar to what we see for the critical zone elsewhere in the Bushveld, mainly very correlatable with the eastern limb. We see a Merensky and Bastard equivalent in places, and this has been published by previous workers. Wolfgang is involved with some of that work. There are fairly clear indications that the stratigraphy is very similar. to the rest of the bushveld, there's a lot of feldspatic rich rocks with these thinner bands of peroxenite which are mineralized. And there's even a UG2 like 1 meter thick chromitite developed towards the base. Then you come across this Planknek-Ysterberg fault. If you look on the right here, where you go across the structure, it's a northeast trending fault into the area further north towards Turfspruit, underneath the town of Mokopane. Things start to change. The peroxenites become far more dominant. As you can see in these areas, you go through towards the Sunslit, the Anglo properties, into the Turfspruit area. So there's quite thick peroxenite, and I think it's important that this has influenced interpretations in the past significantly. So it's something that we looked at very carefully in this whole stratigraphic interpretation for the Platreef. You can see there are zones where there's chrome stringers and sort of poorly developed layers in certain properties. Roger Schoon has published some of that on the Arcanonic property. So these are all things that we looked at very carefully on the Turfspruit area. So these diagrams come out of our paper from 2019 that was in Min Depositor. This just the surface map area for the Turfspruit property. Ivanplats owns the two farms, Turfspruit 241 and Makalakas Pop, which gives us about 6 kilometers of strike on the shallow part of the Platreef. And you can see we've looked at it very carefully from all the drilling that's been done. I'll show you in one of the next slides how much drilling we've actually done on this property. So the holes we're displaying here, the hole numbers, these are holes that have, there's a lot of academic scientific work that has been done in the past few years from Wits University, COFCES, Limpopo University. We've got a collaboration between Limpopo and Laurentian, which is funded by Ivanhoe, which was really successful. There's a lot of work that's been done through that. And also we got Wolfgang Meyer obviously involved here with students, Ian McDonald from Cardiff, with these students. Massive amount of scientific work's been generated in the past few years. And all of this is basically available nowadays. So if you look at how we've defined this, on the shallow part where Ivanplats has drilled out the initial target for the shallow open pit areas, the reef on the contact with the main zone, the green's the main zone. The reef is where you start going to these peroxenitic units, but that was called Platreef. The reef dips fairly steeply around 45 degrees in that area. And then you come across big structures into what we started calling the Flatreef. So in general, this area is quite flat, although there are some undulations that we're seeing. And then across another structure, you come into this deeper portion, what we call the deep Flatreef extension, whatever you want to call it, which goes back to the normal dip to the southwest of this area. So the fortunate thing for us is if the structure wasn't in this area and the dip just continued normally, this whole thing would have not been economic at economic depths. Okay, so this just shows you briefly what was done historically. This whole area here, in this diagram on the left, you can see all the drilling that was done for the open pit areas. They drilled over 500 holes and nearly 200,000 meters. Significant work's been done in this area. But we started moving deeper. We started intersecting some really significant thickness and grade into these areas, and eventually this progressed into this sort of northwestern area, where we really found significant grade and thickness. We did a lot of geophysical work, airborne geophysics, we did 3D seismics, airborne gravity, all these things that assisted us. And we basically defined the area which is fairly flat that extends into this southern area down here. So we actually drilled also some exploration holes in that area. We did a lot of drilling down dip, deeper. Some of our deepest holes go down to 1,800, 2,000 meters in this area. So what we found was that the stratigraphy held together that we defined. Okay, so where are we currently? On our shaft 1, as you guys know, we're busy developing the mine. We started with shaft 1 in early 2015, I think. We also commenced with sinking shaft 2. The foundation of shaft 2 is now completed down to 29 meters. Shaft 1 has gone really deep. We intersected the reef at 781 meters. I'll briefly show you a slide on that. Going through the reefs here, down below into the footwall. So we are currently at 986 meters today. We need to go to 996, so there's 10 more meters to go. Shaft 1 will be completed, the sinking. This deposit is quite big. If you look at the resource classification for our indicated resource, it's very similar to the size of Olympic Dam. And obviously, there's a lot of scope for adding additional resources in this area. Just briefly on the 2 gram cutoff, we've got a 3.77 grams per ton grade, 346 million tons. And on the 2 gram cutoff, contained metal, it's basically 42 million ounces. Again, there's massive upside for this project if we intend to drill additional. Something went wrong now. I lost slides. Was that possible? Just bear with me. The slides are here. Okay, so this just shows you briefly the intersection through shaft 1, the GT8 hole. As we drilled for the geotechnical hole for shaft 1, intersected the reef around the 780 meters. The same happened in the shaft. So it was quite important for us to establish that our downhole surveys were mostly correct. Would have been a small problem if it wasn't. What was interesting is that we saw for the first time in an underground situation what these reefs look like. And that's the first for the northern limb, obviously. So we go through the main zone gabbronorites into neritic cyclical units, as you can see in this picture here, very clear contact onto peroxenite, through down here, this feldspathic peroxenite onto a chrome stringer that we could identify in the sidewall of the shaft into a very coarse-grained pegmatoidal peroxenite, big chunks of sulfide sitting in there. And then in this area, we go directly from this mineralized zone into a footwall where the magma interacted significantly with calcilicates and hornfelses, and you can see that very clearly. So where the magma interacts with sediments, you start to dilute basically and start to disrupt your magmatic stratigraphy and your mineralization. This is a cross section showing you the grades that was modeled. At the top, as you come through the main zone into this first peroxenitic unit, which is about a 4 to 5 meter thick. On this Flatreef portion, it thins when you go up dip, and it starts to thin again when you go down dip. And the mineralization becomes erratic down dip as it does up dip, but on this Flatreef area, the mineralization is not too bad, and it's sitting at 4 meters, running at about 4 grams per ton. So that correlates, if you look at the critical zone elsewhere in the Bushveld, to something that we would think is the bastard reef. We see middling units below that, very similar to what is seen elsewhere in the Bushveld. You go into northern sides, norites, thin peroxenites, and then into this much thicker zone. And this is where the difference comes in on the Flatreef with the rest of the bushveld. We see a very much thicker zone of feldspatic peroxide associated with chrome stringers and a pegmatoid at its base. And this is our high-grade mineralized zone. Below that, you go into areas where there's normal footwall, anorthosites, norites, and deeper down, you start to see mineralization coming in again. So you start to see, you get a picture of more stratiform reefs, which was unexpected for the Platreef. Compared to the rest of the bushveld, this is what we're seeing. We're seeing very significant similarities with mineralized zones and stratigraphy, with the upper critical zone and lower critical zone in the rest of the bushveld. So one important thing I have to highlight here is that a certain distance, depending on where you are on the property, we intersected the 1 meter thick chromitite with its feldspatic peroxide hanging wall, very similar to UG2. And below that, we see a lot of chrome coming into more normal peroxenitic, finer grain peroxenitic units, very similar to what you see on the Eastern Bushveld complex into the lower critical zone. Okay, so the bastard reef, I've shown this in previous talks. I just want to briefly go again through this. We see very similar stratigraphy for bastard cyclical unit, which correlates 100% what's seen elsewhere in the bushveld. The middling units in between, before you reach the higher grade Merensky type reef below that, we see in certain holes erratically developed chrome stringers, below that peroxenite. The middling units, you can see there's certain areas on the property where these units look very similar to the Western Bushveld, Eastern Bushveld middling units, and the thickness are very similar also. And then below that, we go into a Merensky unit. What I need to note is that we also see a lot of what I call soft sediment textures, where these different lithological units seem to slump or interact with each other on a small scale, localized areas. I think I've got a few pictures later on. So very similar to what Seabrook established in the models in 2005. The Merensky itself, I've shown this before. We see in certain areas a thick peroxenite, feldspatic peroxide with very high grade, top loaded, associated with chrome stringers, a typical chromitite stringer at the base on an anorthosite, textbook examples in specific holes. What you need to understand is that in certain areas, this footwall is just peroxenite, like we see in the Eastern Bushveld in some of those compartments. So there's no cyclicity basically there. We do see that in areas across the Turfspruit deposit also. We've done a lot of work on the geochemical data that we had. So basically what we try to do is correlate this again with what we see across the bushveld. We see very similar critical zone signatures, IPGs for these mineralized zones, high tenors, very similar to Merensky tenors, high platinum-palladium ratios at the top of these mineralized zones. Sulfur contents, there's a lot of people that say there's more sulfite in the Platreef. I tend to disagree. I think the reefs are just much thicker, and there are specific reasons for that, mostly controlled by what the magma interacted with, the sediment it came into contact with, and structure also controlling what happened in this magma chamber. So to me, the sulfite contents are not really that much higher. There's just much more mineralized reef in these holes. So these are just some great profiles through a lot of these holes, through Bastard Reef, Merensky Reef. equivalents that we've identified, and you can see there's a lot of variation actually depending on where you are in the property. You can see a basket sitting here in feldspathic peroxide with an autosite at its base. Some of these holes, like I said, showed chromitite stringers there. Then you get the middling units. In a lot of cases on the Flatreef, this middling is just peroxide, but there are areas where there's magmatic cyclical type units. Then you come through the feldspathic peroxide onto the pegmatoid associated with the chrome stringers. You can see the chrome kicks on these contacts. And you can see how these lithological units vary in thickness. Again, these zones are fairly large, so don't think there's massive short distance variation. These holes are picked from different areas on the property. I just tried to show you what type of variation we're seeing across, similar to what's described from the rest of the bushveld. For the Merensky Reef, the way I look at it is that this feldspathic peroxide is, to me, the primary equivalent of the Merensky Reef, and this pegmatoidal feature, this pegmatoidal peroxide or texture, is a secondary texture. So me and Wolfgang, we've been looking at this. We can definitely see how this changes across, and you can get into areas where there's just pegmatoid developed and the entire feldspathic peroxide texture is obliterated, and vice versa. Just a few more examples. I'm not sure how much time I've got. You guys must warn me. Again, these profiles change depending on where you are. Let me just focus on the pegmatoid briefly. The pegmatoidal peroxide, it can be pegmatoidal peroxide, and lower down we see a feldspathic Harzbergite. So these Harzbergite seems to be controlled by the proximity to calcilicate dolomite rafts. And also those fluids appear to be metasmatic and controlled by low angle structures, as we see across the bushveld, as Ian was also mentioned earlier on in his talk. So these structures are quite important. We've done a massive structural interpretation. Albie Brits is busy with a paper that's been submitted to MinDepositor also on that, which is really important. Some more examples. I think I can skip these. There's a lot of academic work that's been done. Kate, that was one of Wolfgang's students, did a lot of work on the Geochem. There's obviously other studies that have also done this. The major trace elements compare very well with the rest of the bushveld. I just want to highlight that. And where we see scatter is where we see the involvement of the sediment, depending on where you are, again, below the reef. So there's definite effect on the geochemistry by these assimilation of and melting of the sediment. And this is quite important. We see two scenarios here. We can go through the main mineralized Merensky type equivalent, the pegmatoid, into a footwall, which is mostly then neuritic cyclical units. But you do see mineralization scattered below into this. And what we found was, when we look at the core in these areas, those are chunks of, well, there is pegmatoidal peroxide developed there that are mineralized. So in some way, in a semi-consolidated manner, these magmas started mixing up with each other and move into the footwall, which is also probably not entirely consolidated. So we do see a lot of textural evidence for magmas interacting with each other. And the other scenario is on the right here. We intersected a hole which had 90 meters of mineralization, significant mineralization, as you can see here, the feldspathic peroxide, high grade, into the pegmatoid, the chrome stringers coming through. But where we do see no grade, basically, is where it seems to be this Merensky pegmatoid assimilated sediment. And that's very clear. So there are zones where the Merensky itself directly comes into contact with sediment. and assimilates and melts it. And I think in a lot of cases there was 100% melting. And we do see that in the shifts that we see when we do the downhole plots on the geochemistry. Okay, there's another one just showing examples here. The Platreef, you can see the chromitite. It's been disrupted basically as the peroxenite and the northside actually interacts with each other. So this is like soft sediment textures developing in these late magmatic units. You can see the angle on the core into the footwall here of the neritic units. And again, there's peroxenite coming through, mineralized peroxenite. So you see erratic mineralization coming through into these footwall type zones. We did a lot of work on establishing in the models the thickness variations. Very important, this pegmatoid, our focus obviously on the pegmatoid because it's the high-grade reef. Where the peroxenite is thick, the Hartsbergite is thinner, and vice versa. So in general, the thickness remains fairly constant for this pegmatoidal reef, but the lithologists don't. And again, like I said, it definitely appears that the Hartsbergite, the olivine-rich unit, is associated with what's happening in the footwall below it. More calc-silicate dolomite xenolith sitting in these areas. So the Deutschland formation, which was the host rock into which this part of the magma intruded, controlled a lot of these things. How these lithologies developed. Okay, just briefly, you can see the lithological variations, also thickness variations, peroxenites and orthosites, the pegmatoid coming through. I didn't put the structure on here because this starts to get quite complicated, but you can see there's a shift in the thickness of the hanging wall to the bastard reef in this area, and then it shifts down to this area where there's very thick pegmatoid of the Merensky developed, and then where the footwall below that is actually quite thick and well developed. So this, we're really looking at this based on the active structure when the magma chamber was starting to consolidate and probably sag, and you can see that this was controlled by the strain in the magma as these things were starting to crystallize, and the shift of the magma chamber as the sagging developed. So there's still work that we need to do on this. But I think it's something that shows you how these lithological variations, you've got to be very open-minded when you drill a hole in this area to really understand what's going on. So just briefly, I don't know how much time I've got.
2 minutes, Danie. Continue.
Oh gosh. So there's a lot of work that was done at Laurentian University with our Limpopo students that were selected, PhDs, MSCs. The one important thing I have to say, and Pedro will also probably talk about that, is we found the same initial strontium ratio kick that was established for the Western and Eastern Bushveld complex at the level of what we correlate with Merensky Reef. So this was quite important. There's a publication also on this that's going to go out in Min Depositor. We've got a thematic issue for Min Depositor that's coming out hopefully later this year. Some of the other trace elements, sulfur, selenium, all these things, plot where Merensky Reef plots. You guys can look at that. Okay, and then Wolfgang looked at this in his talk. We did some age dating also on the single zircons, which are very similar to Merensky again. If these things are out of sequence, I don't know. I think we're looking too much at it in too much detail. We need to look at these things, need to correlate with what we see in the field correlations, the contacts. We need to make sure that things actually make sense. So that's all I want to say about that. So, like I said, Albert Brits is busy and submitted the paper to Min Depositor. There's massive detail that we've done on structure on this property, and you can see the detail on the section here on the left. We've focused on this. We see these low angle features. Some of them have been intruded by late granite dikes and sills. All the structure, the fault zones that we've identified, shear zones. And obviously this is another talk, but we've identified 3 magmatic slump features on the higher up dip areas. So this must have been quite close to the edge of the intrusion. The way we see it, there's a lot of stoping of magma, these different magmatic units, critical zone, low critical zone, lower zone, that's stoped into sediment on the edge of the intrusion. Always modeled the chrome stringers. We're seeing bifurcations, coalescence of these stringers, all sorts of things happening. We obviously focus on that related to the mining that we're going to do soon on this. Okay, so the big important thing here to me, in conclusions, apart from this new stratigraphy, and I didn't go really through this stratigraphic interpretation we've done, because I've done that in the past on talks. But to me, the big thing is we need to start to realize that the PGE mineralization in the Platreef is primarily controlled by stratiform reefs and not contact type processes. This Platreef historic term includes elements of the upper critical zone and probably lower critical zone and lower zone. We see a lot of evidence for that. So what's called Platreef, we cannot just go correlate that directly with the Merensky Reef. That's a big mistake. And that's why the ratios that people look at, the platinum ratios, those things just doesn't work when you do that. So you've got to be very careful how you look at this thing. I would like to acknowledge Wolfgang's involvement, Pedro, Hugo, Matt LeBon, all the guys from Canada, Marina Yudiskaya, Judith, Dr. Harry Parker, our external QPs have grilled us on this interpretation from North America, but I think it was all important. And obviously all the students that have been involved and still are involved. Thank you very much.
All right, thank you, Danie. In the interest of time, we'll just have one quick question. Please raise your hand and then unmute yourself. George, go ahead.
Thank you, Danie, for an excellent talk again. Briefly, can you explain to us how the deposit is being mined? Because you don't have a single reef, you have something that's 29 meters thick. So what type of mining method are they using to exploit the deposit?
Yeah, so we've got 2 reefs. The thinner reef, we're looking at drift and fill, and a much thicker reef, a combination of drift and fill, depending on where you are, the geotech, everything. Everybody's obviously got a massive input here, and also long hole stoping. So these are going to be big stopes. That's basically the way we're looking at it.
Thank you.
All right, thanks. Like I said, any questions? I see some of the